Welcome. Today's lesson is on Pythagorean Theorem, which you probably have talked about before. We're going to do a quick review of what that accomplishes for us. And we're also going to tie in Pythagorean Theorem with what we were talking about the other day, which is triangle similarity. So Pythagorean Theorem deals with the lengths of the sides of a right triangle and how they relate to each other. Little terminology. The legs are the two shortest sides. They also form the right angle. So in our triangle here, we would have leg AC and leg BC. The hypotenuse is the longest side, and it is opposite or across from the right angle, meaning it is the only side that is not involved in helping form the right angle. That's what an opposite side is. Typically, we can name the sides of a triangle one of two ways. You can either name it using the two endpoints on it. So the bottom side of this triangle we could call side CB, or we could also name it using a single lowercase letter that is the same as the angle opposite it. So like these two sides make up angle A. The side not involved in that would be called side A. We use a lowercase a to denote a side, an uppercase A to denote an angle. In a similar way, you could name side AC, just as easily call that side lowercase b. And finally, the hypotenuse here, side AB, could be named lowercase c. All right, well, what this Pythagoras gentleman discovered back in about 500 BC, so about 2,500 years ago, 2,600 years ago, Pythagoras discovered that if you took any right triangle and drew in a square off of each side, and then found the area of each of those squares. Each of these squares, of course, because it's a square, would be as long as it is wide. So this square with length C would also have a width C. This square with a length B would also have a width of B. And this square with a width of A would also have a length of A. And therefore, the smallest square in the diagram, the one on the left, would have an area that is simply length times width, or in this case, length squared, would be b squared. The middle square at the bottom here would have an area of a times a, or a squared. And then the big square, which is based off the hypotenuse, would have an area of c times c, or c squared. And Pythagoras found if you took this big square, this area of c squared square, and then put this medium square onto it, and then chopped up this little square and filled in the spaces, that the big square, the area of that big square would be equal to the two little squares that cover it up. And as a result, he developed his theorem, which says if the legs of a right triangle have lengths called A and B, so this thing and this thing are the legs, and the hypotenuse of the right triangle has a length called C, the Pythagorean theorem states that A squared plus B squared is C squared. What we're going to do now is a bit of an intricate proof that goes through and actually proves Pythagoras' theorem in another way, using similar triangles. And the reason we're doing it is it's a bit academic, of course. I want you to get better at understanding similarity, and I want you to get better at understanding a proof. Now, this isn't necessarily something I would have expected you to come up with on your own, but it is something I'd expected. If we go through it step by step, you can say, yeah, okay, yeah, I get that. that's really the idea here, is just to see a good, 19 step proof, and be able to be on board for all 19 steps. So if you have to stop, if you have to rewind, go ahead. But let's jump in and see what we can do. First of all, I'm going to take the big ABC triangle, and I'm going to draw in from side C, from angle C, I'm going to draw an altitude. So I'm going to run a segment that goes to the opposite side in a perpendicular manner. You're going to want to draw that in on the top triangle of your note sheet. What that accomplishes for us is it gives us really 3 right triangles instead of just 1. Check this out. We've still got our big triangle ABC. I'm going to label that. But what we've also got is a medium-sized right triangle that I'll outline in red. That is triangle DCB or BDC or something. To figure out what goes where, I'm gonna draw it down here. To figure out what goes where, I'm gonna put in my 90-degree angle. That is clearly angle D in the diagram, so I'm going to keep it angle D in my broken apart diagram. And then DC is the short side, so I'm gonna keep DC as the short side in my broken apart diagram. And then the third vertex is B. I will label that. The other triangle that results, that I'll highlight in yellow here, is triangle ADC. And once again, angle D is the right angle, so I will label that accordingly. The short side is AD, so I will label the short side of my triangle, rewrite AD. And the remaining vertex is C, so I will call this C. And now we are ready to go through this proof. The steps have the conclusions have been written out. It is the reasoning that we need to fill in. All right, so let's jump into this thing. I've got to draw my altitude in here, like we had on the previous page. Label that side D. That makes both of these angles D. And then I'm going to label the rest of the angles, as we did before. Let's jump into the proof. Again, there's a lot of steps here. None of them, there's nothing in here you shouldn't already understand. It's just a matter of putting a lot of little things together. So let's tackle it. Angle C in the big triangle is congruent to angle D in the middle triangle. I think we can all see that they're both right angles, and I think we all know that right angles are congruent with each other. Now they're saying angle B in the big triangle is supposed to be congruent to angle B in the middle triangle. Well, that's really the same angle, and anytime you're saying something equals itself or something is congruent to itself, that is the reflexive property. As a result, they're claiming the big triangle ACB is similar to the middle triangle CDB. Well, we've already shown in steps 1 and 2 that they have 2 corresponding angles that are congruent, and that is all you need to show similarity. Now, congruence would be another matter. But for similarity, all you need are 2 angles that are congruent, the 2 corresponding angles that are congruent. So they are similar triangles through AA similarity. Now we're going to go through a similar process in showing that the big triangle is eventually similar to the little triangle. They start out with angle C, that's the right angle on the big triangle, and angle D, that's the right angle on the small triangle. They're going to be congruent because right angles are congruent with each other. Then they're going to state angle A on the big triangle is congruent to angle A on the little triangle. Well, it's the same angle, so yeah, that is again the reflexive property. And now that we have 2 corresponding angles congruent, we can go ahead and say big triangle is similar to little triangle, and again, that's through AA, or angle-angle similarity. All right, now, so far we've shown that big triangle is similar to middle triangle, and we've also shown that big triangle is similar to small triangle. It's kind of like this. If I tell you I am as tall as my cousin Steve, and then I find out by standing back to back that I'm also the same height as you, I can still conclude that you're the same height as my cousin Steve, even though you've never met, because you're using me as really the common measuring stick. That idea is called the transitive property, and it's also why we can conclude that this triangle is similar to this triangle. Because both middle triangle and small triangle are already shown to be similar to big triangle. They are similar to something in common, therefore they are similar to each other. That idea is called the transitive property. And since we've shown all this stuff is similar to each other, we can start writing ratios and proportions. All right, so they are claiming side AC, so the vertical side of, the short side of the big triangle divided by the hypotenuse of the big triangle. Short side over hypotenuse is going to be the short side of the small triangle over the hypotenuse of the small triangle. Short side, hypotenuse. That's a fair statement. And that is frankly just from, that is just a similarity proportion. Oh great, I've got PROP to be in property and proportion. It's a propo. Then they're saying that AC times itself is AB times AD, and that is simply a cross multiplication statement. That's just doing algebra. Now they're going to do something similar for this next ratio. Now they're going to say side BC, which is the bottom of the big triangle, over side AB, which is the hypotenuse. Now we've got middle side over hypotenuse. Middle side over hypotenuse. If we apply that same ratio to the medium triangle, we've got the middle side over the hypotenuse is BD over BC. BD over BC. That is, again, just a similarity proportion. And if you cross multiply, you get BC squared equals AB times BD. All right, number 12 is a little bit of a departure from what we've been talking about, but it's an easy enough thing. They're saying side AB, this massive length here, is really just the product of two smaller segments, or the sum of two smaller segments. Segment AD gets you part of the way across. Segment BD gets you the rest of the way across. If you put it all together, you've got big long side AB, and that is true through what we call segment addition. You may be wondering where line 13 comes from, and that's not a bad question. And the answer is actually a little simpler once you realize just what's going on. What they did was they went back through the proof, specifically lines 9 and 11, and they said, well, wait a minute, in line 9, it says that AC squared can be replaced with AB times AD. So what they did is they said, well, I got this AC squared. I could just as easily take that out and replace it with AB times AD. That's where that part comes from. Then later on in line 11, they said, well, wait a minute, there's an expression here for BC squared. So what I'm going to do is I'm going to take out BC squared, and I'm going to put in this thing that it's equal to. That is where your logic from line 13 comes from. the property that allows you to take out one quantity and put in something equal is called substitution. Very commonly used in algebra without even necessarily thinking about what you're doing. You do that very often. So 13 we've dealt with. What they did to get from 13 to 14 is they said this term has an AB in it, and this term has an AB in it. So they factored out the AB. If you take the AB out of this term, the only thing left is AD. That's why it shows up here. If you take the AB out of this term, the only thing left is BD. That's why it shows up here. This is a process that you should be familiar with. It's called factoring. So we factored out AB in this case. In the next step, they took that AD, here's what's changed from 14 to 15. AD plus BD turned into just AB. And the fact of the matter is, in line 12, AB was equal to those two things. Now we are just literally substituting. AD plus BD is the same thing as AB. That is, again, substitution. You're taking out one thing and putting in something equal to it. And then another way of writing AB times AB is to just say AB squared. So that's, again, that's really substitution. You're taking out one thing and putting in something equal to it. In 17, they're just naming the sides of the triangles. Instead of using two uppercase endpoints, they're using one lowercase letter that we talked about at the beginning of this video. So AC equals little b, BC equals little a, and AB equals little c. I guess we can just call that renaming sides of a triangle. Real official sounding thing, I just made it up. But that's what we're doing. So because of that, AC comes out and B goes in. BC comes out and A goes in. AB comes out and C goes in. And when you do that, you get B squared plus A squared is C squared. So we're really taking line 16 and replacing the uppercase way of naming the sides with the lowercase way of naming the sides. So this is, again, just substitution. And then the last step, all we did was we switched the B squared with the A squared. You can do that. You can add stuff in any order you want. If you think back to your Algebra 1 days, we learned the property for that. Addition is what they call commutative, meaning you can add stuff in any order that you want without changing the final value. Multiplication is also commutative. Subtraction and division are not. But this is what we were trying to prove. I know we took a long time to get there. My hope is that you can kind of follow from step to step what's going on, even if you wouldn't have necessarily come up with it on your own. That's okay. Honestly, I had to think about this a few times before I could put the proof together. But I'm certainly hoping you can follow step to step what's going on. If you can't, you might want to take another look or two at it and be ready to talk about it in class.